And in this video, we're going to look at carbocation relative stability. Okay, so here's the simplest carbocation you can have, CH3+. If you look at the VSEPR rules, we have no lone pair electrons and 3 bonds. Therefore, that tells us that this is going to be trigonal, planar, and sp2 hybridized. And that is, in fact, the structure for CH3+. It's isoelectronic with BH3. Okay, when we were looking at the relative rates for the conversion of alcohols to alkyl halides, we noted that there was an effect of structure, that tertiary alcohols react the fastest, faster than secondary, faster than primary and methyl alcohols. Okay, and I sort of hinted to the structure, to the back then, that we could trace this relative rate effect to the stability of the carbocation. The carbocation forming step 2, where the protonated alcohol loses water to make a carbocation. That is the slowest step of the reaction. That's the one that has the highest activation energy. Since it's a very endothermic process, the Hammond postulate tells us that the transition state is going to look very much like a carbocation. Okay, so we can trace this relative rate to the relative stability of the carbocation intermediates. So this means that this tri-substituted carbocation, or tertiary, is the most stable type of carbocation, or the lowest energy, and we're looking at now isomeric forms of this compound. This is lower in energy than the secondary carbocation shown here, and much lower in energy still than the primary carbocation. Okay, you may wonder, what is the origin of this effect? And it has to do with the contribution of electrons from the adjacent sigma bonds. Okay, so in this structure here, we see how the electrons in the CH bond are perfectly aligned with the p orbital of the carbocation, the empty p orbital. Okay, so this is a center of severe electron deficiency. There's only 6 electrons at this carbon right here, right? Only 6 electrons buzzing around the nucleus. Okay, so this needs more electrons, and it'll get them from unusual places like sigma bonds. Okay, and we refer to this process of stabilization by overlap with adjacent sigma bonds as hyperconjugation. Okay, and hyperconjugation is shown here from the contribution of this CH bond. Notice that this these two CH bonds are not overlapping with the p orbitals. Therefore, they're not, in this structure here, they're not engaged in hyperconjugation, but there's free rotation around the sigma bond, so when they rotate to the place where the depicted CH bond is, they will start to stabilize the carbocation. Okay, this is kind of a hard concept to understand. One of the best ways to understand it is with molecular orbital theory. So if we look at the CH bond over here as being a filled sigma orbital and an unfilled sigma star orbital, and the p orbital as being just an empty orbital at a slightly higher level because it's not engaged in bonding, what we see here is that if we now interact these two species here, we get a net lowering of the energy of the system, and this is what really is the origin of hyperconjugation. Okay, all right, so we're engaging the adjacent sigma bonds in stabilizing the electron deficiency at that carbon. And it's through the orbital overlap of a sigma bond on the adjacent carbon with the empty p orbital. All right, this is kind of a controversial point. I don't necessarily believe it, but some people will say that hyperconjugation is another form of resonance. If you take resonance literally, it can't be, because you've broken a CH bond, or you've changed the connectivity. If it's not connected, then it can't be a resonance structure. But there's still some degree of connection here. All right, so what we're looking at here is where that CH bond basically now becomes just an alkene with a H plus or free H plus in the vicinity. Okay, like I say, I don't necessarily believe this is resonance, but this is one way to think of hyperconjugation. All right, and when we get more of these CH bonds involved in these types of processes, we get more stabilization. Okay, so I put the question here to just to remind you that there's not necessarily everyone believes that these qualify as resonance structures. Okay, all right, so when we go to the secondary carbocation right here, what you see is that there's two ways you can write this. So there's more resonance, or there's more of this hyperconjugative stabilization when you have a group on either side of the carbocation that has sigma bonds attached to it. And when you get to the really stable tertiary carbocation, of course, you have three groups that can contribute in this way. So this is the origin of the stability. Okay, now I did a calculation using a program called Gaussian, and this is the structure of the primary carbocation. We can see how it really does it justice, right? Because here we have, there's our H plus. It's kind of just somewhere out in space. It's like an H plus complex to the simplest alkene of them all, ethylene, whereas it becomes more of a carbocation-like structure when you go to the secondary carbocation, but notice that there's still partial multiple bonding indicated by the bond links in this structure. All right, so yeah, so the hyperconjugation, again, it's not, I can't really tell you the perfect way to look at it, but just remember that since a carbocation is such an electron deficient intermediate, it will steal electron density from unnatural places like sigma bonds. Okay, so here's a type of problem. Predict the relative rate for these compounds reacting with HI. Some of them are kind of close. On an exam, I tend to eliminate species that have ties. So, but since this isn't graded, we can explore some deeper issues here. Okay, all right, so I'm going to call these compounds A, B, C, D, and E, and if you haven't remembered how I told you to do these problems, try to do them yourself, pause the video, then restart the video. All right, so we're looking at which of these is going to react with HI the fastest to produce the corresponding iodide. Okay, so what's involved here, of course, is we're really only looking at the carbocations. Okay, so here's the carbocation. I'm just going to draw them as C. Okay, that one's already kind of just a C. Okay, now we're looking at the degree of substitution. Here we have at that carbon an alkyl, another alkyl, and another alkyl, no hydrogens, so we're going to call this one tertiary. Here there's two hydrogens and an alkyl group. This one is primary. This one has a hydrogen and two alkyl groups. This one's secondary. This one is also tertiary because it's got three alkyl groups. And this one is also secondary because it's got two alkyl groups and a hydrogen. So that's a secondary. Okay. Another thing I want to caution you about was drawing carbocations and intermediates that are charged, or as we're looking at the next section, free radicals. Don't draw the bond line formula in the presence of the carbocation. It kind of leads you to confusion. Okay. So we're looking at which one of these will proceed through the most stable carbocation. We're probably going to say A and D are going to be the fastest because they're tertiary. This one has a CF3 and this is electronegative. And that's the difference there. All right, so between A and D, we're going to predict that A is going to go faster because of this electronegative stuff here. We have a partial positive at this carbon, and we're getting a full positive and a partial positive a little bit too close to each other, so that's destabilizing it. So we're going to say that A is number 1. D is number 2. Okay, there's really no way to distinguish probably between C and E. They're both secondary and there's no special considerations here. One of them's a little closer to the more substituted group, but that's not really going to affect how fast they form. Okay, so C and E we're going to say are pretty much tied at number 3 and 4, and B should be the slowest because it's a primary carbocation involved in that substitution reaction. Okay, so here just summarizes what we said here, and here are the easy ones, the best, the second best, and the worst, and these two are kind of tied. Okay, all right. Let's look at a special case. We said that with tertiary and secondary alcohols, the mechanism that you see at the top, which we presented and talked about in the previous video, is in fact the generally accepted mechanism. It's a first order reaction, and we're going to give it this reaction symbol SN1, substitution nucleophilic first order. And we're going to revisit this issue of SN1 in chapter 8, okay, when we talk about substitution reactions. All right, so the kinetics of this process are a little bit different with a primary alcohol. With a primary alcohol, there's only 2 steps. So the first step is the same, where the product of step 1 is the protonated alcohol halide anion pair. And in step 2, the reaction actually finishes. What's occurring here is that in a concerted fashion, as water leaves, bromine comes in. Okay? Now, in this case, this is the rate determining step, and you see that the halogen is involved in the reaction. The rate here is second order because it involves both of the reactive species, and we refer to this as an SN2. So methyl and primary halides typically react by SN2. For all practical purposes, only iodides really work very well with primary halides and methyl halides. Okay? Superior reagents have been invented for transforming primary alcohols into the corresponding chlorides or bromides. Okay, so if you want to turn an alcohol into the corresponding chloride, the superior reagent to do this is thionyl chloride. All right, if you want to turn a primary alcohol into the corresponding bromide, this transformation right here, the preferred reagent for doing that is that. So we're transforming the OH group into the Br group with PBr3. We're transforming the OH group into the Cl group with SOCl2. These are the balanced reactions. We will discuss them much later when we talk about what we call ester formation in a much later chapter. Okay, you may say, well, they're slower, but if we're patient, can't we just wait longer? We're going to see in the next chapter that another process becomes very important that makes it kind of detrimental to even try to use HCl or HBr to transform a primary alcohol into the corresponding primary halide. Okay, all right. We say that alkyl groups, we're going to use a special term for these. Electron donating groups, commonly abbreviated in this class as EDG. They stabilize electron deficient intermediates like carbocations. That's what defines an electron donating group. We're going to refer to carbocations as electrophiles or Lewis acids. They're reacting with things that have electron pairs, like in this case, halide ions. Okay, so primary and methyl halides, we don't get typically good yields, as we said before. And again, here's more or less a repeat of that alternative mechanism. This is actually complete, so even though it's a repeat of the previous slide, let's just look at it in its entirety. All right, so step one, we make protonated alcohol. In step two, we don't want to do this, right? This is not good because this carbocation is too unstable. So this SN2 pathway takes over, and we see the concerted second order process that involves both species, the halide and the alcohol or protonated alcohol in the reaction. Okay. All right, so here's a classic type of problem that you see in this class. It's called what I call the three variable, two given, you supply the third variable problems. Predict the products of each of these reactions. All right, so PBr3 we've seen as a reagent that just turns ROH into RBr. So we just take our alcohol group and transform it into the corresponding halide. And that's what we now have right here. Okay, so we just transform the alcohol into the halide. HCl reacts with a tertiary alcohol in this case here. And we know that this is a reagent that as long as a reasonably good carbocation intermediate is involved, this is a good reagent for turning the alcohol into the alkyl halide. Okay, so since this is a tertiary alcohol, we expect the OH group to transform into the corresponding chloride group, and that is in fact all that happens. Okay? All right, this is a compound where we're very carefully adding exactly 1 mole of HI, and we have two alcohol groups, a tertiary alcohol and a primary. Okay, so the relative rate says that tertiary alcohols are greater than secondary, greater than primary. So remember that relative rate. All right, so we're going to react at the tertiary alcohol right here, and this is going to be replaced by an iodine, and that gives us this product. Don't be fooled by the fluorine, okay? That doesn't do anything. We have not discussed any reaction of an alkyl halide with another with HI. So sometimes we do this where we put unreactive functional groups. You just have to know when to ignore them, okay? And this is one that you can safely ignore. All right, here we're turning the alcohol into the halide, and we notice that the alcohol is primary, so HCl would not be the right choice. SOCl2 is the only reasonable choice here, and this is because it's a primary alcohol. Okay, since it's a primary alcohol, we need to use SOCl2 instead of HCl. Okay, and here's a final problem that we're going to do here, and this is what we call a mechanism problem. A good answer to a mechanism problem typically depicts every reactive intermediate or every energy minimum, if you remember the big potential energy diagram for this reaction before. It would use proper arrows as we discussed earlier in this chapter. Okay. Also, another hint is when organic professors start drawing lone pairs at oxygens, they often intend for you to use them. Okay. And one other thing I have to stress about a mechanism problem. Don't use anything except what's in the reaction equation, okay? A lot of people will bring reagents like potassium hydroxide or things like that into the reaction when they're not part of the reaction equation. We should be able to accomplish this reaction using nothing but HI and the starting material or any of the intermediates that are generated in any of the reaction steps. Okay, so the answer that's going to get 100% of the credit here would involve protonating the alcohol with HI. Okay, another hint that's there is pretty valuable is also that the benzene ring is unreactive. We're not going to see benzenes really do anything for quite a while. Okay. All right, so you have to draw this compound, okay? I'll draw it. I'll just be very careful to draw all the lone pairs for a while here. Okay. All right, we'll draw them all at iodine too, all 8 of them. Okay, in this step, we need to form the carbocation. And this should be a pretty good carbocation. It's tertiary. Okay. And it makes water. This actually has some other stabilization from the benzene ring, but don't worry about that for now. All right, this iodine that we generated in the first step, it's just watching the second step happen. Okay, so this we'll say step 1, step 2. Okay, so step 2 involves no iodine, but it's still there. Okay. And in step 3, which is a very fast step of the reaction, we're just adding the iodine to the carbocation. This gets rid of all the intermediates that don't have octets, and this is a very favorable step. Step 2, remember, is our rate determining step. This reaction should be pretty facile because we have a tertiary alcohol. Okay, all right. Sorry, I guess I've already done this one. Sorry, I didn't even need to do that for you. Sorry, but there's the reaction mechanism printed out. Okay, with officially drawn structures instead of hand-drawn structures. Okay, so my computer drew those structures. Sorry about that. Okay, all right, so I think this is the last slide in this video. Okay, energy minima. Okay, remember that we have to show all of the reactive intermediates, so it's essential that we show the protonated alcohol, the and the carbocation. These 2 intermediates have to be shown to get all of the credit for the answer. Okay, and this is where we're going to end this video right here.